In mathematics, the continuum hypothesis is a hypothesis about the possible sizes of infinite sets. It states, there is no set whose cardinality is strictly between that of the integers and the real numbers. The continuum hypothesis was advanced by Georg Cantor in 1878, and establishing its truth or falsehood is the first of Hilbert's 23 problems presented in the year 1900. I currently see the answer to this problem is independent of ZFC set theory, so that either the continuum hypothesis or its negation can be added as an axiom to ZFC set theory, with the resulting theory being consistent if and only if ZFC is consistent. This was proved in 1963 by Paul Cohen, complementing earlier work by Kurt Gar-Paragraph Dell in 1940. The name of the hypothesis comes from the term the continuum for the real numbers. It is abbreviated CH. Cardinality of infinite sets. Two sets are said to have the same cardinality or cardinal number if there exists a bijection between them. Intuitively, for two sets S and T to have the same cardinality means that it is possible to pair off elements of S with elements of T in such a fashion that every element of S is paired off with exactly one element of T and vice versa. Hence, the set has the same cardinality as. With infinite sets such as the set of integers or rational numbers, this becomes more complicated to demonstrate. The rational numbers seemingly form a counterexample to the continuum hypothesis. The integers form a proper subset of the rationals, which themselves form a proper subset of the reals, so intuitively, there are more rational numbers than integers, and more real numbers than rational numbers. However, this intuitive analysis does not take account of the fact that all three sets are infinite. It turns out the rational numbers can actually be placed in one-to-one correspondence with the integers, and therefore the set of rational numbers is the same size as the set of integers. They are both countable sets. Cantor gave two proofs that the cardinality of the set of integers is strictly smaller than that of the set of real numbers. His proofs, however, give no indication of the extent to which the cardinality of the integers is less than that of the real numbers. Cantor proposed the continuum hypothesis as a possible solution to this question. The hypothesis states that the set of real numbers has minimal possible cardinality which is greater than the cardinality of the set of integers. Equivalently, as the cardinality of the integers is and the cardinality of the real numbers is, the continuum hypothesis says that there is no set for which, assuming the axiom of choice, there is a smallest cardinal number greater than, and the continuum hypothesis is in turn equivalent to the equality. There is also a generalization of the continuum hypothesis called the Generalized Continuum Hypothesis which says that for all ordinals. A consequence of the continuum hypothesis is that every infinite subset of the real numbers either has the same cardinality as the integers or the same cardinality as the entire set of the reals. Independence from ZFC, Cantor believed the continuum hypothesis to be true and tried for many years to prove it, in vain. It became the first on David Hilbert's list of important open questions that was presented at the International Congress of Mathematicians in the year 1900 in Paris. Axiomatic set theory was at that point not yet formulated. Kurt Gar-Paragraph Dell showed in 1940 that the continuum hypothesis cannot be disproved from the standard Zermelo-Eurofrankel set theory, even if the axiom of choice is adopted. Paul Cohen showed in 1963 that CH cannot be proven from those same axioms either and Cohen. Hence, CH is independent of ZFC. Both of these results assume that the Zermelo-Eurofrankel axioms are consistent. This assumption is widely believed to be true. Cohen was awarded the Fields Medal in 1966 for his proof. The continuum hypothesis is closely related to many statements in analysis, point set topology and measure theory. As a result of its independence, many substantial conjectures in those fields have subsequently been shown to be independent as well. So far, CH appears to be independent of all known large cardinal axioms in the context of ZFC. The independence from ZFC means that proving or disproving the CH within ZFC is impossible. Gar-Paragraph Dell and Cohen's negative results are not universally accepted as disposing of the hypothesis. Hilbert's problem remains an active topic of research. See Woodin and Koellner for an overview of the current research status. The continuum hypothesis was not the first statement shown to be independent of ZFC. An immediate consequence of Gar paragraph Dell's incompleteness theorem, which was published in 1931, is that there is a formal statement expressing the consistency of ZFC that is independent of ZFC, assuming that ZFC is consistent. The continuum hypothesis and the axiom of choice were among the first mathematical statements shown to be independent of ZF set theory. These proofs of independence were not completed until Paul Cohen developed forcing in the 1960s. They all rely on the assumption that ZF is consistent. These proofs are called proofs of relative consistency. Arguments found against CH. Gar paragraph Dell believed that CH is false and that his proof that CH is consistent with ZFC only shows that the Zermelo-Eurofrankel axioms do not adequately characterize the universe of sets. Gar paragraph Dell was a Platonist and therefore had no problems with asserting the truth and falsehood of statements independent of their provability. Cohen, though a formalist, also tended towards rejecting CH. Historically, mathematicians who favored a rich and large universe of sets were against CH, while those favoring a neat and controllable universe favored CH. Parallel arguments were made for and against the axiom of constructibility, which implies CH. More recently, Matthew Foreman has pointed out that ontological maximalism can actually be used to argue in favor of CH, because among models that have the same reals, models with more sets of reals have a better chance of satisfying CH. Another viewpoint is that the conception of set is not specific enough to determine whether CH is true or false. This viewpoint was advanced as early as 1923 by Scullom, even before Gar paragraph Dell's first incompleteness theorem. Scullom argued on the basis of what is now known as Scullom's paradox, and it was later supported by the independence of CH from the axioms of ZFC, since these axioms are enough to establish the elementary properties of sets and cardinalities. In order to argue against this viewpoint, it would be sufficient to demonstrate new axioms that are supported by intuition and resolve CH in one direction or another. Although the axiom of constructibility does resolve CH, it is not generally considered to be intuitively true any more than CH is generally considered to be false. At least two other axioms have been proposed that have implications for the continuum hypothesis, although these axioms have not currently found wide acceptance in the mathematical community. In 1986, Chris Freiling presented an argument against CH by showing that the negation of CH is equivalent to Freiling's axiom of symmetry, a statement about probabilities. Freiling believes this axiom is intuitively true, but others have disagreed. A difficult argument against CH developed by W. Hugh Woodin has attracted considerable attention since the year 2000. Foreman does not reject Woodin's argument outright but urges caution. Solomon Furman has made a complex philosophical argument that CH is not a definite mathematical problem. He proposes a theory of definiteness using a semi-intuitionistic subsystem of ZF that accepts classical logic for bounded quantifiers but uses intuitionistic logic for unbounded ones, and suggests that a proposition is mathematically definite if the semi-intuitionistic theory can prove. He conjectures that CH is not definite according to this notion, and proposes that CH should therefore be considered not to have a truth value. Peter Koellner wrote a critical commentary on Furman's article. Joel David Hampkins proposes a multiverse approach to set theory and argues that the continuum hypothesis is settled on the multiverse view by our extensive knowledge about how it behaves in the multiverse, and as a result it can no longer be settled in the manner formerly hoped for. In a related vein, Saharanchila wrote that he does not agree with the pure Platonic view that the interesting problems in set theory can be decided, that we just have to discover the additional axiom. My mental picture is that we have many possible set theories, all conforming to ZFC. The Generalized Continuum Hypothesis. The Generalized Continuum Hypothesis states that if an infinite set's cardinality lies between that of an infinite set S and that of the power set of S, then it either has the same cardinality as the set S or the same cardinality as the power set of S. That is, for any infinite cardinal there is no cardinal such that GCH is equivalent to. For every ordinal, the Bethe numbers provide an alternate notation for this condition. For every ordinal, This is a generalization of the continuum hypothesis since the continuum has the same cardinality as the power set of the integers. It was first suggested by Giordano, 1905. Like CH, GCH is also independent of ZFC, but Sierpinski proved that ZF plus GCH implies the axiom of choice, so choice and GCH are not independent in ZF. There are no models of ZF in which GCH holds and AC fails. To prove this, Sierpinski showed GCH implies that every cardinality n is smaller than some Aleph number, and thus can be ordered. This is done by showing that n is smaller than which is smaller than its own Hartogs number. Kurtgar paragraph del showed that GCH is a consequence of ZF plus V equals L, and is therefore consistent with ZFC. As GCH implies CH, Cohen's model in which CH fails is a model in which GCH fails, and thus GCH is not provable from ZFC. W. B. Easton used the method of forcing developed by Cohen to prove Easton's theorem, which shows it is consistent with ZFC for arbitrarily large cardinals to fail to satisfy much later. Foreman and Woodin proved that it is consistent that holds for every infinite cardinal. Later Woodin extended this by showing the consistency of for every. A recent result of Kami-Marimov showed that, for each Na per mil 1 yen, it is consistent with ZFC that for each I, 2I is the nth successor of I. On the other hand, Laoszla cubed Pater, 1930, proved that if I cubed is an ordinal and for each infinite cardinal I, 2I is the I cubed th successor of I, then I cubed is finite. For any infinite sets A and B, if there is an injection from A to B then there is an injection from subsets of A to subsets of B. Thus for any infinite cardinals A and B, if A and B are finite, the stronger inequality holds. GCH implies that this strict, stronger inequality holds for infinite cardinals as well as finite cardinals. Implications of GCH for cardinal exponentiation. Although the generalized continuum hypothesis refers directly only to cardinal exponentiation with 2 as the base, one can deduce from it the values of cardinal exponentiation in all cases. It implies that is, page 147, exercise 76, when I plus or minus a per mil currency I squared plus 1. When I squared plus 1, I plus or minus and where CF is the cofinality operation. And, when I squared plus 1, I plus or minus and. See also, Aleph number, Beth number, cardinality, I copyright logic, references, Cohen, Paul Joseph, 1966. Set theory and the continuum hypothesis. Meineuer, New York, Dover Publications. ISBN A978-0-486-46921-8. Cohen, Paul J. The Independence of the Continuum Hypothesis. Proceedings of the National Academy of Sciences of the United States of America 50, 1143 doi, 10.1073/FNAS 50.6.1143. JSTORA 71858. PMCA 221287. PMIDA 16578557. Cohen, Paul J. The Independence of the Continuum Hypothesis, 2. Proceedings of the National Academy of Sciences of the United States of America 51, 105 110 doi, 10.1073/FNAS 51.1.105. JSTORA 72252. PMCA 300611. PMIDA 16591132. Dales, H.G. Woodin, W.H. An Introduction to Independence for Analysts. Cambridge, Dowburn, Joseph Warren. Georg Cantor, His Mathematics and Philosophy of the Infinite. Princeton University Press PPA 134 137. ISBN A9780691024479. Enderton, Herbert. Elements of Set Theory. Academic Press, for Furman, Solomon. Is the continuum hypothesis a definite mathematical problem? Exploring the frontiers of independence. Foreman, Matt. Has the continuum hypothesis been settled? Retrieved February 25, 2006. Freiling, Chris. Axioms of Symmetry, Throwing Darts at the Real Number Line. Journal of Symbolic Logic 51, 190 Euro 200 doi, 10.2307/2,273,955. JSTORA 2,273,955. Gar paragraph del, K. The Consistency of the Continuum Hypothesis. Princeton University Press. Gilman, Leonard. Two Classical Surprises Concerning the Axiom of Choice and the Continuum Hypothesis. American Mathematical Monthly 109. Gar paragraph del, K. What is Cantor's Continuum Problem? Reprinted in Banasaraf and Putnam's collection Philosophy of Mathematics, 2nd ed., Cambridge University Press, 1983. An outline of Gar paragraph del's arguments against Ch. Goodman, Nicholas D. Mathematics as an Objective Science. The American Mathematical Monthly 86, 540 Euro 551 doi, 10.2307/2,320,581. MRA 542,765. This view is often called formalism. Positions more or less like this may be found in Haskell Curry, 5, Abraham Robinson, 17, and Paul Cohen, 4, Hampkins, Joel David. The Set-Theoretic Multiverse. Reverend Sim. Log 5, Number 3, 416 Euro 449. Seymour Hayden and John F. Kenyon, Zamilo Euro Frankel Set Theory, Charles E. Merrill Publishing Company, Columbus, Ohio. Jerdin, Philip E. Beyond Transfinite Cardinal Numbers of the Exponential Form. Philosophical Magazine, Series 6 9, 42 Euro 56 doi, 10.1080/14786440509463254. Koellner, Peter. The Continuum Hypothesis. Exploring the Frontiers of Independence. Koellner, Peter. For Fermat on the Indefiniteness of Ch. Cunan, Kenneth. Set Theory, An Introduction to Independence Proofs. Amsterdam, North Holland. ISBN A978-0-444-85401-8. Maddy, Penelope. Believing the Axioms, I. Journal of Symbolic Logic 53, 481 Euro 511 doi, 10.2307/2,274,520. JSTORA 2,274,520. Martin, D. Hilbert's First Problem, The Continuum Hypothesis, in Mathematical Developments Arising from Hilbert's Problems, Proceedings of Symposia in Pure Mathematics XXVII, F. Browder, Editor. American Mathematical Society, 1976, ppA 81 Euro 92. ISBN 0-8218-1428-1, McHugh, Nancy. The Continuum Hypothesis. Marimovich, Kami. A power function with a fixed finite gap everywhere. Journal of Symbolic Logic 72, 361 Euro 417 doi, 10.21781185803615. Moore, Gregory H. Early History of the Generalized Continuum Hypothesis, 1878 Euro 1938. Bull. Symbolic Logic 17, 489 Euro 532 doi, 10.21781318855631. MRA 2,896,574. Schiller, Saharan. Logical Dreams. Bull. Amma. Math. Soc 40, 203 Euro 228 doi, 10.1090 per second 0273-0979-03-00981-9. Woodin, W. Hugh. The Continuum Hypothesis, Part 1. Notices of the AMS 48, 567 euro 576 Woodin, W. Hugh. The Continuum Hypothesis, Part 2. Notices of the AMS 48, 681 euro 690 German Literature, Cantor, Georg. Ian Beitrag zur Mannigfaltig Kiezlu. Journal Far 1 Quarter die Reine und Angewandte Mathematik 84, 242 euro 258 doi, 10.1515/CRLL. 1878.84.242 Partei, Untersuchungen 1 Quarter die Rehe. Mathematische und Naturwissenschaftliche Berichterstattung 37, 127 euro 142 External links, Zurzik, Matthew and Wettstein, Eric W., Continuum Hypothesis, MathWorld. This article incorporates material from Generalized Continuum Hypothesis on Planet Math, which is licensed under the Creative Commons Attribution Share Alike license.